My dear friends, today I'm going to discuss with you how we can derive the formula of time period of simple pendulum. And for that, first of all, you have to remember a formula for acceleration in SHM. The acceleration in SHM is minus omega square y. You know very well, omega is your angular velocity, which is 2 pi over t, and y is instantaneous displacement. And negative sign here, negative sign shows that acceleration is always directed towards the mean position. Okay, this is a formula of acceleration, and in magnitude it is omega square y. Negative sign we have neglected because it is just magnitude part. Now from here omega square comes a over y. Omega is root of a over y. And what is omega? 2 pi over t. And we can find out the value of t from here. 2 pi under root of y upon a. That means the formula of the time period of the SHM is 2 pi under root of displacement divided by the acceleration. We can use this formula of the time period in any example, in any case, if it will be confirmed that that case is of simple harmonic motion only, then we can use this formula of the time period of the SHM. Okay. Remember the formula, very easy, no problem. 2 pi under root of displacement divided by the acceleration. Now we're coming to the oscillation of the loaded spring. Before going to discuss the simple pendulum, this is a rigid spot. This is a flexible spring and a mass is attached at here. And the frictionless surface on which the mass is placed. Okay, it is assumed that the surface is frictionless. We pull the mass towards the right by some distance y. You know what happens? A restoring force comes into play. Okay, which opposes the pull. So that restoring force always proportional to y, and this restoring force will try to bring the spring back to its original position, original configuration. Negative sign mean force is restoring, and it is exactly opposite to whatever. If it is extension, it will be along opposite in direction, maybe extension, maybe compression. The force will be opposite to extension or the compression always. That means this is a restoring force. Okay, and by Newton's second law, F is mass into acceleration, and A from here becomes minus k over m into y. You know, this is a formula of the acceleration for a spring. And acceleration in SHM was minus omega square y. Now comparing the equation 1 and 2, comparing the two equations, it is found that omega is under root of k over m. You know, omega is 2 pi over t, and t becomes 2 pi over 2 pi m upon k. What is m? M is inertia factor. This k is called, spring constant or the spring factor, because it comes in case of a spring. This constant involves in spring. So m is the inertia factor and k is the spring factor. Remember this formula, very important for the time period of a spring if mass is attached and if it is pulled by some distance y. Okay. Now we're coming very, very important article. There's a simple pendulum. Now the one question for you, why it is called simple? So we are having a thread or a string. There's the earth surface. Okay. Thread or the string having some characteristics. The string or the thread should be weightless first of all, and it should be inextensible, perfectly flexible. These are the properties. Okay, perfectly flexible. Here is a point mass which is attached at the lower end of the string. Point mass doesn't mean less mass. Mass may be 1 quintal, but in dimension it should be a point. And let it is displaced by a distance y. This is again a string, and this is a point of suspension, and the center point of the point mass is called point of oscillation. Distance between the point of suspension to the point of oscillation is called the length of the pendulum, L. So this is L. Okay. Now next. This is a weight mg perpendicular to the earth surface. So mg is resolved into the components. One component along the string produced onwards, other is perpendicular to they are rectangular components. If this angle is theta, corresponding angle this will be theta. So this component will be mg cos theta, and this will be mg sin theta. And there will be a tension in the thread because there's a mass is attached with at its end, so that's why there's a tension. Again, I'm repeating, mg components, theta, mg cos theta, mg sin theta. Okay, tension T. mg cos theta balances with the tension. So T in magnitude becomes, in magnitude of mg cos theta, both are equal and opposite forces, but they are exactly equal in magnitude. Mg sin theta is only unbalanced force, and it pulls the point mass back towards the mean position. So that's why this force is a restoring force. What is a restoring force? That is mg sin theta. So that's why it is written with negative sign. Now sin theta is having a expansion. Very well about this expansion. Now, in approximation, we considered that sin theta approximately theta, neglecting the higher terms because of the smaller magnitudes. So sin theta is approximately theta. Now, this is y, this is L. Angle is written as arc over radius. Angle is theta, and arc is y over L. Now, substituting theta here, theta is y over L. F becomes minus mg y upon L. F is mass into acceleration. Cancels out. A becomes g upon L into y. Now this A may be written as big A as it is acceleration. G upon L is constant. Okay, and acceleration comes out directly proportional to displacement. So that means oscillation of a point mass, simple harmonic. So that's why now we can use the formula of the time period of SHM. So T is 2 pi under root of displacement over acceleration. Okay, substituting A here, and time period becomes 2 pi y upon A. What is A? That is, okay, y cancels out, it becomes L over G. Now that's the last formula, L upon G. Okay, very important. Now time period is quite independent of the mass of the bob. That is, there is no expression, no term of mass. So time period directly proportional to square root of the length only. So T increases with the increasing the length of the pendulum with the square root of L. So what it But it doesn't mean if L tends to infinity, then T also tends to infinity. No, no. So this expression is not valid for infinite lengths because the expression was under approximation. So this is only valid if the length of the pendulum is less than the radius of the earth. Okay, so only valid if the length is less than the radius of the earth. Otherwise, no. Okay, if the length is greater than the radius of earth, it is not applicable. So this is all about the time period of the simple pendulum. Okay, thank you.